When you hear the applause, you know it's time to start. Good morning. I'm going to start on time today because I need to be out of the building at 10:30. So we'll get going right away. And as usual, I want to start with today's AI news of the day. And I found this really interesting, which is that SynthID, which is a watermarking technology made by Google to watermark images and LLM-generated text, both, is being used by NVIDIA to watermark their large world models. Now, a world model is basically a three-dimensional representation that your LLM can reason about, or more importantly, your robots can think about as well. So they're very interested in how do we represent spaces and devices and things that move in the world. And what NVIDIA is doing wants to watermark everything that's generated in that world model. When we come back to robots in a few weeks, we'll talk more about what a world model is. But I just found it interesting that they feel the need to copyright and mark these things, so that if you, unsuspecting researcher, go off and borrow someone else's world model, they could potentially say, oh, I see the watermark, this is actually mine, and come after you for it. So it's an attempt to do digital rights management, DRM, for models of the world. We'll see how far this goes, because as you probably know, the history of DRM is not great. Every DRM approach has been broken over time, either by collective action or by a very smart hacker somewhere. So we'll see whether or not this actually has legs. But it doesn't stop people from trying, and they will continue to try. So copyright management, DRM management, is a thing with us forever and ever. Amen. So the other interesting piece of news this week has been this post by Ethan Mollick. At the very last class, we will talk about how to stay up to date on progress in the area. Ethan Mollick is one of those writers you should pay attention to. So there's the link in the slides, which you have access to through the syllabus, where he talks about what he calls post-apocalyptic education, which means us. We are living in the post-apocalyptic educational world. And he's talking in this article about how students learn and don't learn and all this stuff. But he points out an interesting thing, which is, as you can see from the chart, basically all homework can now be done by some language model. The other interesting thing about this chart is that the system that scores the best is a blend, it's a multi-model system, okay? So that's what the gray bars are here, one that's scoring 100% in advanced practice biology in the US. So all the AP courses are advanced classes. So homework is one of those things that either you could just hand it out to your AI agent and have it do it for you, or you could actually learn it. Remember the illusion of learning. The fact that you've typed in a query into an LLM and got an answer and copy-pasted that into an assignment that you give to me doesn't mean you've learned anything. Right? So this is one of those things. And he points out in this article this really interesting graph I hadn't seen before. This is from an older article, which is the number of copiers of people who are copying things out of Wikipedia or online resources into their homework has gone up from roughly 10% back in 2008 to roughly 60%, and this only stops in 2018. Prediction, it's gone up since then. And all these students are not getting the point of their education. So let me tell this to you, and I tell this to my kids, I will tell it to you. Education is hard. Learning is hard. If it's not hard, you're not doing it right. You need to actually put in the cognitive effort and feel that friction, okay? Feel the friction as you learn. Otherwise, you're not really learning. Okay, so speaking of learning, this is where we're at. The reason, oh, darn it, I didn't include the next 2 weeks. Well, Tuesday, we're going to talk about fairness again and bias and ways to analyze it and detect it in your data sets. Cool. And then the next week, we're going to talk about the next day, we'll talk about data lifecycle and the issues with that. And then the next two classes, which are not on here, are about parts 2 and 3 of natural language processing for voice user interfaces, which I'll mention today, and conversational user interfaces. So how do we do those? Here's the foreshadowing for that. It's complicated. You can't just invoke ChatGPT and think you're done. So we'll talk about why that becomes more interesting and more challenging. Okay? So let's talk about human-computer interfaces in general, bleeding into natural language interfaces. Now, there are entire courses on this, and you can find a lovely course that's online from Stanford by Chris Manning, who does nothing but for the entire semester talk about natural language interfaces. There's bunches of people doing things like this. Today, we're going to kind of give you an overview, and I'm going to give you a little history, how we got into this state. And the reason I'm giving you all this history is that people who do not remember the past are condemned not just to repeat it, but to make stupid mistakes. I was in a meeting at Google a couple years ago where bright young UX researchers said, hey, I have invented a new technique. It's awesome. And he describes it, blah, 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 blah. And I said, you know, I have a patent on that technique. I patented it about 10 years ago when I was at IBM. And so not only is it's a great idea, I patented it, but you can't use it unless you're going to pay IBM the royalties for it. So one of the things you have to remember is that there are lots of good ideas out there, but a lot of them have already been explored. And so that's the point, really, of teaching the little bit of history we're going to talk about today. Okay? So I'm going to go way back. So these women here in front of little computational devices were the original computers. That's where the word comes from. So these people who sat in offices and did pieces of computation on adding machines with paper and pencil were the original computers. And so the word derives from them. And so she's actually using a slide rule, which is a wonderful analog computing device, which I had to learn in gymnasium. But that's where that came from. And then, of course, computers at the time looked like that. They were huge. They were difficult to use. But the first programmers were the ENIAC girls. So that's the term we used at the time. And the computers at the time had about 50 flops, which I know is like my watch has at least a megaflop in it. So it's one of those things where things get better. And she's working here. These are actual programs on wire boards. So that's what a program looked like. And so we then moved into, at about the same time, punch cards came into being. So punch cards are basically, this kills me, actually. A piece of interesting history you may not know. Hollerith cards, invented a long time ago, like in a previous, multiple centuries ago. They're this size. You know the size of, you get tickets like this? Do you know why they're that weird aspect ratio? Because they're exactly the same size as these punch cards. And so a bunch of machineries in the world to handle paper cut to that size. And it still persists to this day. So it's a little bit like roads from the Romans still persist. We still travel on roads that were made by Romans. We still use pieces of paper cut in the format of 80-column cards. I used to program using punch cards. It was a major pain. Editing a program meant finding the card with the wrong statement in it, punching a new card and slipping it in. God help you if you dropped your deck of cards, right? Smart programmers, I will tell you, this thing over here, these last 7 columns, you could punch a sequence number in it, right? 1, 2, 3, 4. And then there's another device where you could sort the cards by whatever column you want. So you could sort by this. So you drop a box of cards. A box is 2,000 cards. So it's a typical program length. You drop it. It's a mess. You put it in. You sort it. You're done. Okay. And you very quickly learn not to number your cards sequentially. What are you going to do if you're numbering them 1, 2, 3, 4, 5, and you need to insert between 3 and 4? 10, 20, 30, 40. Do not insert more than 9 cards. All right, get the idea. And so this was actually one of my first programs because I'm old enough to actually have worked on these kinds of devices. So this is a programmable accounting machine. And you would create a program by moving data literally from this field over to that field. So that's a copy-paste operation on these devices. It was fantastic. Notice also 80 columns. Guess why? These things persist. So let's go forward a little bit. So now you know about operating systems that have been out there, Mac OS, Linux, et cetera, et cetera. Even though we only think about these 3 operating systems today, there are endless operating systems in the world. There really are. Lots of them run on very small devices, so you get very special purpose. Say the ARM chip has an OS, or the devices that run on, for example, the Google Assistant has its own OS. Chrome OS is another OS. So Google alone has 3 OSs that it built. I don't know why. I mean, I know technically why, which is that there are 3 different teams, and they didn't want to wait on the other team, so they built their own OS. That's the way large companies work, just saying. So you end up with this plethora of OSs, which you know about. And the nice thing about some of these, like with, say, a Linux shell, is that you can do really, really powerful things through text, which looks like language. Right? I'm telling you that because there are things like this awk statement right here, which allow you to do really, really wonderful things. And as you probably know, moving directories inside of Linux is much simpler than like dragging and dropping folders on Mac OS. So the OS and its affordances, remember that word, affordances? The affordances of the OS allow you to do things more easily than not. This is important as we go into natural language. Think in the back of your head, what does natural language allow me to do? What's simple to do and what's difficult to do? So we have all these OSs, and they come out. Neil Stephenson wrote this book about the beginning of the origins of command line. If you haven't read it, it's worth reading, just to get a sense of how this all came to be. Fast forward a little bit. I was at Xerox PARC when we invented the graphical user interface. There was a time before the graphical user interface. Right. There's an interstitial point in there when programs will be written on teletypes. After cards, before Windows like this, you would actually type in a long series of commands to create a piece of code that was in the machine, like think of a classic piece of code. But to edit it, you edited it on paper. So imagine what that interface is like. You would give commands like, go to line 49 and replace the word X with the word Y. And then it would go and give you that, and you believed that it was right. But the cost of refreshing the display, like printing out the program again, was really high. I mention this because costs, that is the amount of time it takes you to do something, or the difficulty of remembering how to do it, those costs turn out to be important in UI design. That's true for natural language as well. Anyway, we've got all these things. We've got these kinds of interfaces, and life is good. Ultimately, in 1984, the Mac comes out. It looks like that. And I want to point out something interesting to you. You may not recognize this, but that's a floppy disk. So that's actually a storage device, okay? And then a little bit later, the Mac had these more fancy interface devices. And this is an icon design called skeuomorphic, S-K-E-U morphic, M-O-R-P-H-I-C. It's supposed to be looking like the thing it's replacing. So this is the radio app, this is the messaging app, this is the phone app, et cetera, et cetera. You probably have noticed that we don't do that much anymore, but that was the thing. So you get these trends and these sort of fashions in UI design. Trust me, natural language interfaces are going to go through similar cycle. So one thing you should be thinking is, what is the current style of a natural language interface? So as you use your natural language devices over the next, say, couple of weeks, notice the style. Is it skeuomorphic? Is it trying to sound and behave exactly like a human, or is it trying to do its own thing? So skeuomorphic design got crazy. So you could click, for example, on the news app, and it would give you, this is not a picture, this is a rendered UI, where you can see all the different magazines that were available in your collection. Yeah.
What I'm thinking currently is like, isn't it all still there is skeuomorphic design? Because when I think about it, if I want to pick a call on my phone, it still has the small, how you...
The handheld headset, yeah.
Or if I want to speak to NLP, to a national GPT, you still have the voice, not the voice, but the mic symbol.
Yeah.
So we still have the skeuomorphic, even if it's a bit iconographic.
No, that's the right way to think about it. So the question here is about, don't we still have this kind of symbols in our UIs? And the answer is yes, we do. But as you point out, they're more iconic, more schematic than skeuomorphic. Skeuomorphic says that you actually, for example, there's wood grain here. There's wood grain in the UI. Why? I don't know. It looks cool, right? Or you actually have little drop shadows here behind each of the magazines. Icons don't have drop shadows, right? So it's very appealing, and I want to give you a key concept. A key concept going forward for you is you can build all kinds of stuff that demos well but doesn't work. Demos well but doesn't work in reality. And I have seen endless numbers of very cool systems that demo really well, and when you try to use them day to day, do not work out. This is one of those. So things go on, and then we start to develop UI idioms, so standardized ways of interacting with these things. So you probably know about double click, select, drag, et cetera, all those things, right? So when we have now handheld devices with a touchscreen, a multi-point touchscreen, it's important, you can actually do things like rotate. So you know all these, right? These are, you're the digital generation. These are all as mother's milk to you. They're sort of built into your fingers. I know that I double tap on something, I long tap on something, but people slightly older than you don't remember double tap. They don't understand what double tap or long press means. So, for example, I've seen people on their phone accidentally long press on an application icon. Speaking of which, nice demo. And it starts, all the icons start to wiggle. You know that mode? And they go, oh, I've broken it! Because they don't understand the idiom. They don't understand the language, the way that's being represented. And so for a skeuomorphic thing, real magazines don't wiggle around like that when you want to move them, right? But that becomes a UI idiom. And so in some sense, the history of user experience design is searching for the idioms that people understand and can use to control their systems. So we've got, those kinds of things. And this is still a skeuomorphic design, right? So you get a blend. Nothing ever switches 100% all at once. Sorry, over here. Right. So the trash can still looks like a trash can, dang it. But you get these idioms that you can use to interface. So now we get to more conversational, more voice-driven user interfaces. And there's a bunch of different devices here that you can talk to. When you look at this device, what's the natural affordance? Well, you have to know it's a speakable device. Okay? So the reason they all have this sort of pattern on the outside is it looks like a speaker. When these devices were first introduced, they were sold as smart speakers that you could talk to. Okay, and actually on the inside, if you tear one of these open, you'll see a whole ring of microphones around the outside. And they do various clever beam-forming techniques to actually pick up what you're saying. So if you're on this side versus this side, the microphone effectively switches around to the other side, right? So there's a lot of interesting engineering that goes on in order to give you a good experience. So you don't know about the beam shifting, the microphones. That's the audio engineer's problem, but it's crucially important because if it wasn't there, You'd walk over to the other side of the device and it would stop working. Right? So there's an interesting interplay between the engineering, the lowest levels, and the user experience at the highest levels. So we've got this. What's the biggest issue in voice user interfaces? Discoverability. Right? Now, I have to give Apple a lot of points because they have taught an entire generation of people how to speak to Siri and how to say what kinds of things you can say. By contrast, Google has botched it. They screwed it up. What Apple has done is through their advertising, they've engaged in a mass education campaign. If you watch carefully, all of the ads for Apple or Siri and so on show you how to do it. They tell, there's not, here's how you do it, step one. It's more like, here's Billy, and he's doing this to ask about his calendar for today. Isn't that great? And you pick it up. You pick up the language through observation, right? And Google will say things like, we have a massive multi-layered machine to do calendar prediction. And that's it. They don't show you how to do the things that are marvelous. So immense capability, terrible education. Terrible. So discoverability is the primary problem for a lot of the voice interfaces. How do you know what you can say to it? Do not reply, you can say anything, because you can't. Although that's changing, right? It's actually getting to a point, probably in a couple of years, you actually will be able to say almost anything. But at this point, you still can't quite say anything. So the question for us as designers of AI systems, how do you teach the world what it can do? So a complaint I often have about my phone is, my phone has all these functions on it. There's a button on here that allows me to do almost anything. Maybe I can speak to dead people if I could only find the button, right? So mostly what people say is you could just search for it. And actually, funny story happened yesterday. I was downtown at some chocolate shop, and I was buying a little thing of chocolate. And there was an interesting symbol on the package. And I said to the guy, what is this symbol, right? What does this mean? He said, I don't know, but you could Google it. And I thought, I literally wrote the book on this. So he didn't know that. It was just unintentionally funny. But it was one of those things. How do you discover the discoverability of these things? How do you figure it out? So one of the things is, we've got all these devices and we've got these different styles of presenting things. And there was this really nice paper from a couple of years ago which said that an approach is to build in a narrative. Storytelling. So a key lesson of this entire course is also that stories are important. Stories are important for communicating capabilities, and in fact what this is several frames of a story showing you, the user, how this little monster figures out how to use all the capabilities. So there are other ways to do this, but this is a really nice one. Developed how? Wizard of Oz studies, just so you know, right? There are other devices, and I can go on and on about this. There's a whole series of classes I can give you about the history of HCI, but on wrist devices, right? I have one that I've been wearing for about 20 years, the same one, and it's a classic dumb watch. It's not smart. Someday I will get a smartwatch, and I will be just like you. But at this point, it's not quite what I want. The interesting thing about all these devices is that half of them are abandoned after 6 months. How many of you, raise your hand, if you bought a Fitbit or something and gave it up after a few months? Okay, a few of you actually hang on to them, awesome. But we know from the return rate from the devices, it's about 50%. So it's sort of interesting. So the other thing to point out is it's really interesting history of phones, with these phones, right? Which is that this is a giant function magnet. What I mean by that is we still call, at least I still call it a phone because I want to call somebody on it. The number of times I actually used it as a phone, tiny. right, is very, very small. I mostly text, or I WhatsApp, or any of the other millions of things. But what's happened over time is that the cell phone has adopted more and more sensors and more capability. So, for example, nobody buys a step tracker, right? Why would you buy a step tracker? That used to be a little device you put on your belt. Now it's built into my phone. There are accelerometers in the phone. So that function has been absorbed into the phone. I don't carry a camera much anymore, unless I'm really doing something special, looking for birds or something. But mostly I rely on my built-in camera, et cetera, right? I read books on here, so you see where this goes. Over time, this thing has absorbed more and more capability. So that's kind of cool. And one thing that's fascinating is that applications in China, for example, you have the super apps, right? Which do everything, right? You can do messaging, you can do financial transactions, do everything. By contrast, in the US, every app is a different thing. And various people have tried to do super apps in the US and it has not worked out. So it's interesting cultural expectation differences. So now we're in the age of chatbots, right? Welcome to the 2020s. And we got this thing, and this is, I guess, ChatGPT. And you can ask reasonable questions like this. Why is the sky blue? And you'll get a reasonable answer. And what I want you to think about for the next couple of minutes is, what kinds of applications can be best done with chatbots versus a special purpose user interface? Think about that and talk to your neighbor here for we'll just give you 3 minutes. What do chats do really well, and what do they do poorly? Go. Okay, everybody. I'm dying to hear your insights. What do you know now? You've all just been chatting, right? What is chatting a really great UI for? This is where you answer. What do you think? What are chatbots really good for? What's a good application? Pardon? Companionship. Okay, that's a very interesting one. It looks like you're nodding. Do you agree? Yeah.
Extracting information. For example, in psychology, you want people to talk about themselves, and if you just want to write about your own, for example, values, you don't do anything. But if you talk to someone, then you easily get information out of you.
So, getting information during a conversation. In fact, that's a really good point, because one of the fascinating things about having a chat with a chatbot for medical purposes like medical history is that people are much more revealing of their internal state to a chatbot than to a person, which is really weird, but really true, okay? So it turns out that people are totally happy to say, I have a pain on my body part that I can't say to a human, but I will happily say to a chatbot, right? So that's a really interesting observation, okay? Anybody else? Yeah.
We also said search, because like Perplexity, for example, like it still contains context. So if you write the next
Okay.
Google it.
This is a great observation. So chatbots, or things like Perplexity and so on, you can actually write out a very long query, which would be a disaster with Google, but works quite well with Perplexity because of the context. It's one of those weird things about search engines. The more terms you put into a query, the more diffuse the analysis becomes and becomes less focused. But chatbots like Perplexity actually use that additional context to provide information for the search, which is what people do. So that's a really great point. What are chatbots terrible at? Anything? Math? True, but we're getting better at that. But that's a good point. Anything else? What are they terrible at?
Customer service.
Customer service. Man, I totally agree with you on that. I've had many long chats with chatbots, and I end up saying, "Give me a human." You've probably done the same thing, right? In this case, it's actually interesting because the context is bigger than just the query than you're trying to do, right? The other problem with them, as we'll see, is that they will often overpromise on things they can't actually deliver. So it's an alignment problem for the AI. Okay, good point. So here's a little bit of the background here. So we got these devices, you talk to them, and a bunch of stuff happens. And to first order, you can start to get words out of the speech signal. You can sometimes get speaker ID, you can get the location, certain amount of emotion, emphasis, and sarcasm. Now, let me tell you the reality. That's what you hear, right? Let me tell you the reality is that we actually, in the speech reco world, do really well on words, and we're getting better at speaker ID and location. But these three, And the problem is not that the signal's not there. The signal's totally there. But understanding, interpreting the signal, especially the prosody, the voice changes, right? So there's this classic funny story about a guy goes to a linguistics conference, and the speaker says, all languages of the world have double negatives. So you can say no, no, and that simply intensifies the negative aspect, right? And he says, but there's no language known where you can do a double positive and intensify the positive. And somebody in the back says, yeah, right. Okay? Why is that interesting? It's a funny story because the prosody carries a lot of the information. It's clearly sarcastic, right? So there's another book you should know about, another book I recommend, just because it's fun, The Diamond Age. Because in The Diamond Age, Neil Stephenson talks about this online tutor that is your tutor for life. So it basically grows up with you. And it basically has this voice user interface that provides a very easy, personalized educational experience. And all the issues we talk about come to life. They also have these things called media glyphs. So only the very elite classes can actually read text. Everybody else goes through the voice user interface, the VUI. And the interesting thing is Stevenson did not imagine that speech reco would get to where it is now. So everything was done with mechanical Turk voice actors. So barring that, okay? So I want to show you a little video clip because it highlights exactly this point about what you get from speech recognition systems. Now, if you do any programming at all, you've probably built a little device so you can actually write some code, call a speech reco API, and you'll get back the words, the string, or what was spoken, or what was recognized, right? But But a lot of those systems do not carry the additional information, like the emotional status, the prosody information, the notion of sarcasm, etc. So watch this little video clip and see what happens here.
When did you shoot him?
Video clip.
What? At what point did you shoot the clerk?
I shot the clerk.
Yes, when did you shoot him?
I shot the clerk.
Hey, Dean, we need you out here. I'm in the middle of a damn confession here.
Whoa! Wait a minute!
Fast forward
I
cut.
asked him if he
Courtroom.
did it, and he said, I shot the clerk. I asked him again, and again he said, I shot the clerk.
Your Honor, no further questions.
Do you see a problem there? The problem is the prosodic content is not reflected in the transcript. And what's more, when he's on the stand, he doesn't put the prosody back in. So the judge doesn't know. It sounds like a pure confession. He doesn't know that the kid is actually asking that question rhetorically, sort of in disbelief. So there's an interesting issue for us here. Yeah. There we go. So when we're doing voice interfaces, when we're dealing with natural language, you constantly have to think about what the uncertainty in the signal is. And there's uncertainty that you can get, like, I wasn't sure what the word was, but most of the APIs, not all of them, but most of them just say, here you go, here's what I heard. And if it's something like, listen to this. How to recognize speech. Question, what did you hear me say? How to recognize speech. Did you hear me say A, how to recognize speech? Or did you hear how to recognize speech? Right? The phonemes are almost identical. And so it's 50-50 what your speech record system will give you as the string. What a better voice record system would do is give you the uncertainties. So here are 3 or 4 different parses of what I heard, going from the phoneme to the words to the phrases and so on. So this is what people do, because when we're, for example, my German is terrible, so when I'm listening to somebody in the shop say something, and they will say something, and I don't recognize a couple of the words, but I get the rest of it from the other words I do recognize, and I can fill it in and go, oh yeah, she meant that, right? And so that sort of interpolation of interpretation is important. So we can ask questions in the user interface to clarify. You don't need to write the code so that it just takes in the string and tries to do the right thing. You can actually take an action. So here are some actions. So when you have very low certainty, you do an implicit confirmation. That's Monday the 14th. At what time? Ask a question. Do the clarification step. Now this requires the UI to do something, right? This is why a large language model does not completely solve all known natural language problems. So we can do a lot of things like that. I'm just going to run a little bit of this because this is a thing called Dialogflow. It's a Google AI offering, and it basically allows you to build these multimodal natural language interfaces. And so you create a dialogue consumer agent, and you can give it all these different states. So when you pick up the phone and you start talking to your annoying customer service agent, right, you always start in the start state, and then you branch and do appropriate things. Okay, so let's watch a little bit of this.
For us humans, conversation is natural. It's a part of our everyday life. We fundamentally understand it and all the nuances around it because honestly, it's part of who we are. This is why trying to teach a machine to have a conversation is so difficult. It's all about conversational experience. Okay, Google, what's the weather like tomorrow?
In Mountain View tomorrow, there will be scattered showers with a high of 59 and a low of 46.
How you interact with machines right now seems pretty simple. You just ask something and the machine responds. But it turns out that this is a really hard thing to get right for a machine, since people ask for information in various different ways. For example, to do something as simple as get the weather, you could say, "What's the forecast like today?" Or, "What's the weather right now?" Or, "What's the temperature like in San Francisco tomorrow?" Now, if you were to code this traditionally, you'll most likely need a whole matrix of conditionals to figure out all the edge cases for all the ways your users can ask for the single information. But as you can imagine, that's not really maintainable. This is where NLU, or Natural Language Understanding, comes in. NLU is a technology that helps translate human language into computer language and vice versa. It's very similar to natural language processing, but it goes a step further to understand conversations that it hasn't been trained to understand, like errors, spelling mistakes, accents, sentiments, which makes NLU a great fit for chatbots. And what's really nice is that NLU works with both voice and text. Now, NLU is very similar to machine learning, but it's not the same thing. Rather, ML helps drive NLU by... Actually, we'll talk about this in a later episode.
It's so annoying when people say it, but we'll talk about that in a later class. You probably heard me say it. So I want to bring this up, this image here. So we've got AI, which is this super thing, right? And within that is machine learning, and there's deep learning, et cetera, et cetera. There's all these different AI technologies. And we, in the class, are trying to figure out how do we get this into the heads and the hearts and hands of humans. So the class is all about making that interface, literally, between the technology of AI and the experience design, okay? All of this class is not really about building yet another interesting ML model. It's really about how do people understand these things. Okay.
For us human...
Yes. Okay, so as she alluded to in that little phrase, there's been a lot of work over building natural language understanding systems over the years. And as she gave you that example, there's a million different ways to ask for the weather. Now, the way most modern language models work is they kind of coerce that into a point in very high dimensionality vector space, and that has all the semantics around it. But there's a lot of different things one can do here if you're trying to build these multimodal natural language interfaces. So there's speech reco and speech synth models. We're not going to talk too much about speech synth for a couple of weeks until we get to conversational stuff. But the speech synthesis stuff is not the same as speech reco, right? They're very, very different things. And there's a lot of interesting HCI issues in designing those. So there's all these things you can do, and basically there's a bunch of technology available from all these vendors about building chatbots, primarily oriented towards building customer service bots. Sorry, but that's the way the world is going. And eventually they'll start to get better, and that's all fine. So in the history of these things, we've had these, come on. Why isn't my mouse? There it goes. We had CLIs, command lines, we had GUIs, all this stuff, and now we've got these voice interface things. An edit got lost here. Sorry. So one of the considerations we need to think about here for natural language interfaces is accessibility, because not all your users will speak or see, but also we need to think about cultural components and international issues. Now, this is really obvious in Switzerland. This is not obvious in California, right? If you support English and Spanish, you're done. Right? That doesn't work for the rest of the world. And so we'll talk, again, we're going to come back to accessibility of these things. Because some of the work that's been done in the past couple of years for accessibility is just truly astoundingly good. So there's been a bunch of work in that area. It's very, very good. Okay, so here's the trade-off, right? Think about this. You all know how to speak. You all know how to speak multiple languages. But you learn that naturally, and it has a pretty low failure rate. So normal communication like we're doing now, the misheard word rate is quite low. maybe 1% or so. Okay? Text, on the other hand, right, is something you had to learn really, you had to spend years learning how to read, years learning how to write. And if you write in, say, Chinese and English and German, that's multiple orthographies, multiple spelling systems. It takes years, right? So you have this huge investment. Whereas learning to speak, if you learn your languages early on, it's pretty straightforward. You don't have to work too hard at it. It's little cognitive effort. So on the other hand, dictation can be 3 times faster than typing. How many of you feel, just out of curiosity, how many of you feel that dictation is faster than typing in your experience? Yeah? Okay. This is one of these things that's going to change over the next couple of years as speech record systems get better and better. We are going to increasingly shift towards a dictation user interface style because it really is faster. The hang up is when you say something incorrect, tell my wife that I love her. No, don't say that. Say, I really love her. Right? So the correction there, you don't want the word really to be in the text that gets sent to my wife. Right? It actually should auto-correct based on, so the system has to know when you're saying an edit action versus text action, right? So these will get better and better over time. It's also interesting to think back historically. In the 50s and 40s, executives often had assistants that could take dictation. And so the executive would say to the secretary, I need you to take a letter, blah, 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 blah. And all this stuff would happen, right? So my mom was an executive secretary like that, and she knew this magic shorthand writing system. So she could write as fast as the executive could speak. This is a skill we as a culture are going to reacquire, is that ability to speak and make the prose come out well at the end. So anyway, there are these different properties here. Text is slower to produce, but it's faster to ingest, and there's all kinds of interesting summarization capabilities, right? My friends who read Chinese tell me that they can get the sense of a block of text more simply than we can in English, and I kind of believe them. So it's also, text is in general easier to skim, and you can search for keywords a lot more simply.
What do you mean by 20% of most?
20% of? Oh, 20% of the population in the US only has very basic skills, right? And so I don't actually know what the ratio is here, but in the US, there's a huge number of people who only have basic capability, like reading up to 6th grade level. And so when you're designing UI that's going to be used by everybody, you need to take that into account. Okay? So you can't use certain language, certain concepts, just not there. So you see what happens, right? As we build increasingly smaller devices, they grow increasingly capable, until we get to the point now where basically we have ubiquitous computing dependent on cloud services, right? Because my phone doesn't do much on its own, but it does a huge amount because it can tap into the global compute surplus. But we're starting to build even smaller devices. So some people have an Aura ring or a watch that measures various capabilities. Like the phone, the watch is going to be an on-person device that will increasingly get more and more capable as better and better sensors get into it. So right now, the Apple Watch can sense heart rate and all those kinds of stuff. Heart rate variability, for example. Some of the new ones can measure blood pressure. I don't actually know how it works physically, but they claim they can do that. Yeah.
Yeah, it's still limited. For example, blood pressure, you have to calibrate it regularly.
Yeah, I know. But they claim they got a new technology, which I don't understand. We'll see. We'll see. Pardon? And I'm getting there. And oxygen saturation. Yeah. So there's a lot of technologies. So the Aura ring, the watches. Google had this device for a while that measured glucose through a contact lens. Another comment.
It's maybe an excellent case because then we have the problem with the human-computer interface. The computer gives you all those values, but the human can't make any sense of it. Like, what can you do if your O2 level in the blood is now like 90 compared to normally 98?
Yes. So there's a project here, right around the corner, that's working on exactly that problem, specifically for diabetics. So there's a bunch of, so you bring up an interesting point, which is we've got all this data, what are you going to do with it? How do people understand it? Right. So we're building more and more competent, more interesting devices. And of course, the question for us as human designers, people who worry about the experience people have, is who gets the data and who gets to own it and control it. So do you get the FANG companies doing this? Is it you, or what extent do you actually control your own data? Now, right now, you can actually go through and turn off data sharing with all kinds of stuff, right? How many people actually do that? Not very many. Not very many. Not enough to affect the data statistics. That's the interesting thing. So if you're a big company, Amazon or Google, you know that 90% or more of people will leave the default modes on, which basically spills all the data, right? So we've got the, already done that. So we've basically been building these natural language systems like this, where you've got an automatic speech recognition system that then creates strings, which then get put into a dialogue state tracker to figure out what the moves are in the conversation. And so at each point you create a representation of what got said, a representation of the conversation, and then actually what the action was here, so what the policy was, can I actually answer that question or not? And you go round and round and round. So you then end up with a conversation down there, text to speech. Here's an interesting point to remember. We'll talk about this again in 2 weeks about when we talk about voice interfaces. But we think about the cycle like this. So spoken, reco, action, feedback to the user. And that's the basic natural language processing cycle. That's not what people do. In particular, I could say something, and as the system is generating a speech back to me, I want to say something instead on top of it. This is called barge in. Barge in is a key concept for all spoken language systems. If your system does not support barge in, you're not going to make it in the marketplace. It's a terrible non-feature to not have. So barge in is the ability for the human to interrupt by speaking on top of the NL system. So in the old days, a few years ago, what would happen is that the voice interaction would then generate representations of actions like this. So greeting, you want to inform somebody of something, you request it. And so this is the internal representation that these systems, the AI system would have. And so you can eventually, so for example, do an affirm action here. Affirm that we've heard what we've heard, and we want to do this thing next. So there's all these representations. And of course, with all these things, we've got, this is again a repeat slide, we've got all these things you can do to inform people about their uncertainty. But ChatGPT and the language models are not quite the same as this. So when we talk about voice user interfaces, we'll talk explicitly about what the representation has to be that goes along with this. Because if you're in a conversation trying to get something done, say with a customer service agent, you need an internal representation of that. So let me ask you, spend a couple of minutes to think about what else is captured or not captured in a text transcript of a speech. I've already given you a bunch of clues here. Just a couple more minutes and think about that, and we'll keep going here in about 3 minutes. Okay, go ahead.
Because we're humans still
All right. What have you got for me? What have you got? Yes, in the back. Sorry? Irony. Irony. Excellent one. Anybody else? Yeah.
Deception? So deception of
Deception.
person's lying.
Okay, deception. That's good. These are both sort of higher level analytical things, right? So what else? What else is not captured in? Yeah. Yeah, tonality, prosody. Yeah, that's right. Emotion, right.
Any non-verbal cues?
Nonverbal cues, right. So, yes, right. That transcript does not capture this sense, right? Yeah, exactly right. Yeah. Confidence, that's great. It's sort of the opposite of it, right? So there's a lot of the emotional or the affective side of speech that's not represented. Now, I predict that our representations will get better, and you'll start to get APIs to speech ecosystems that will come with decorated pieces of prose, saying, you know, the third word here is said in a higher pitch, or the sentiment of the whole sentence is ironic or deceptive or something. Okay, so we'll start to get to that. There's multiple things that go on here. One of which is that the ambiguity in the recognition is not represented, but the higher order things like puns or deception, those are just not there, or irony, right? So good. Okay, let's switch to talking about language models. So we've got all this technology lying around. Here's the basic linguistics 101. There's all these different layers of linguistics, right? Again, this slide expands into an entire year-long course, but you know, for today we're going to talk about this. So there's this notion that you've got speech, and text and speech are not the same. We just talked about that. Speech breaks down into phonetics and phonology, so how things sound. Text has orthography, that is the way you write it, the way you write the word in a particular language or a particular character set. So for example, we all might write in Latin characters, and I would write word in English in Latin characters, but you could use IPA, the International Phonetic Alphabet, which is another representation which captures the sound. So the way, for example, I would say the word almond is not the way somebody from 100 miles east of me would say it. So I live on the West Coast, California, and I say almond. And if you go 100, so say, 200 kilometers to the east of me, they say almond. IPA would capture that difference. And so it captures accent differences and dialectical differences and so on. That's orthography. So morphology, now we're getting to the level of words and how words are broken up or put together in pieces. So German is famous, for example, for having lots of words concatenated together. So to understand that, you see the different pieces and collectively understand what that word means. Pieces. That's the word as a whole. Lexemes are the individual subunits. Syntax is the way words go together. Functionally, you have verbs and adverbs and so on and so on. The semantics then is the meaning behind all of this. And then you would think, for a long time, people sort of thought that was it. Everything above that was good. And then people started realizing there's a whole pragmatic layer, how speech is actually used in real life settings. And then at the deepest level is discourse. So how do people have conversations back and forth? So here, for example, we'll just talk about a really simple view of the sound system. So I might have a word like detrimental, which is then be broken up into pieces like that. And the problem is, how do you, shoot, there's something missing there. What I wanted to show you is the sound signal for this. So for example, for your sound signal for this, and then and they look very, very different, but we hear them as the same word. So we have fairly sophisticated sound analysis systems in our heads that do all of that mapping. And increasingly, again, computer systems are getting better at doing that. But of course, what happens, the how to recognize speech example, you get a stream of sound, which is then broken up into tokens, which we think of as words. Okay? Tokens in LLMs are kind of not quite the same as words. We'll talk about tokens, foreshadowing again later, but they're sort of sub-word level. They're like 3 or 4 characters long. So you would take a long word and break it down into, say, 4 or 5 tokens. But people, when they're dealing with this, break up the words into tokens that they can deal with and then do an analysis of it. So you look at a word like, a phrase like this is a lifetime sentence, and you have identify that as being present tense, and that is a compound word, et cetera, et cetera. You then can break it down into naming all the pieces of that sentence into determiners, verbs, adjectives, and nouns. And this is where classic linguistics was a couple of years, say 10 years ago. You have these analysis systems. And the history of natural language, the quest was always, how can we build smarter and better versions that would create these analytical diagrams like this? So you create these systems that do various natural language things. We then get all this role labeling so we can understand the semantics. Awesome. The reason I'm telling you all that is to set you up for this. Okay? So here is Eliza. We've talked about Eliza before, 1966. It's a very simple representation of a conversation. So it's a representation of a discourse and what to do. So given you've got this keyword in the sentence that the user typed to you, right? You do this based on what that triggers. So this is an action to take to create a response. It's dead simple, like I said. So that's the simplest possible discourse model. Keyword triggering, pattern instantiation, back and forth. The illusion of life is great. It works really well, right? It doesn't go anywhere. There's no structure to the discourse. It's just call and response, back and forth like that. Okay. Now that, if you, my friends, will recognize as a regular expression, right? So this, what does that represent? Does anybody know? Can anybody read regex? No? It's non-trivial, right? Nobody grows up speaking regex, right? But this is the recognizer for email address, right? So you got a bunch of characters over here as an @ sign, a bunch of characters, a dot, a bunch of characters, end, right? So there are ways to represent this, and then of course we've got these tokenizers that do this. We'll do this same kind of thing in Python. So now, if we think about a language in the context of information retrieval models, like say Google search, you have ranking of results by relevance and quality. So in some sense, Google search is a very simple back and forth conversation. And so when you give a query to Google, it takes all the language in the world, analyzes it, and says, oh, here's the most relevant page, and we rank order those results. This is the most relevant out of 100. Right? And so it doesn't require meaning. So all of this stuff is measured by all kinds of exogenous properties, not necessarily the meaning per se. So relevance, for example, is measured by term frequency, and quality is measured by the coherence of the text in the document which you can write, by the reputation. This is all what page rank is all about, right? So there's a lot of processing you can do of language. Doesn't require understanding. So you might have heard about this, these different models for language. This is the old bag of words model. It's great, very simple to implement. So take your text, put in, just count the number of instances of a word, throw it into a bag, and then do queries or questions about that with respect to just that statistical model. Awesome, except you lose all the sequence information, you lose all the semantics. Semantics is gone, right? But you can still do things like identify the sentiment of the phrase or the collection of words in there. And it works modestly well, and this was state of the art not too long ago. But then we moved forward and we went to n-gram models, okay? So you can, for example, build pieces of text like this and identify the word boundaries, break it up into characters, do it byte pairs, and so on and so on. And then, of course, you get into different problems. Remember I said international consonants matters? Okay, what's exactly a word in Chinese? It's a little difficult, a little more complicated. So there's interesting issues here. So we can start, however, to think about n-grams. We've got these classical definitions of unigram and bigram, and you can have k-grams. The reason I'm telling you all this is because we're going to do something with it in a second. You can estimate probabilities between tokens or k-grams by just counting a bunch of text, right? Notice here, we're not dealing with words now. We're dealing with tokens. So k-gram would be 3 or 4 k-gram, right? So the same notion of token as in a large language model. So this leads to a set of tokens that you can actually do something with. And Andrej Karpathy wrote this paper a while ago now, basically in 2015 saying these recurrent neural nets are going to be important someday. And he was absolutely right. So it turns out that building recurrent neural net models of k-grams that you've got in this giant training set are unreasonably useful. So I want to show you this. I'm going to skip over the Goldberg thing. This is actually a link to a Python notebook, which you can open up and look at. And so this is my co-teacher, Peter Norvig, built a whole notebook here you can go and explore. Make a copy, you can diddle with it all you want. But what's fun about this is he takes the model of a generative language model based on a k-gram analysis of the corpus of Shakespearean text. And as you look through this, you can get down here and actually you can run all this stuff. I'm not going to run it now, but if you're interested in this, this is an easy way to get into it. You can actually go and see exactly how he does the training, exactly how he does it, and then he does a bunch of data structure stuff, and this is the first generation. And he goes, the rest of it is all about if you change different parameters, how the generation gets worse or better. Really interesting stuff. Oh, now I guess the real question is, where did my slides go? Oh. You'd think this would be easier. Where did my slides go? It's here somewhere. Okay, so I need to go to slides. There we go. Okay, so as an example, if you use that notebook and train it on the Bible in English, using a 4-gram model, you can actually then say, recreate these statements about computer science in the language of the model I just gave you, right? And so you get these wonderful things. The direct, bottom line here, the direct utility estimation is an instance of the general algorithm, which the new function is constrained on the fly. For example, the first child of the Holy Ghost, blah, 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 blah. Right? You see where this is going. The model infuses the sense of what it's all about when you build these models like this. How are we doing? We're not going to have time enough to do this, but what? Yeah, let's go to this. I'm going to skip over this, but these things are marvelous, and you can replace the Bible, for example, with the Shakespearean corpus, and you will end up writing all of your text in a Shakespearean voice. And this is one of the ways that you can get voice models, or rather writing voice models, built into your natural language system. So this is really, really marvelous stuff. So, as you know, language models tend to be auto-regressive, and I'll define what that means in a minute, where you train on a model, and then it generates text that's kind of like the text it's already seen. Okay? So, if we have more time, which we don't today, I would ask you this question. If the prompt is to write an essay discussing the role of metafiction work of Italo Calvino, there's a very nice ChatGPT response. The question is, what's the model doing? Is it retrieving text or is it generating a text? Okay. So, as we know, these things are generating, right? So this is an important paper. It's in your reading list. If you haven't read it, I recommend spending at least 10 minutes with it so you can talk about it. This is by a bunch of people who are critics of AI, and the critique they give in this paper is that the stochastic model, that is, the classical ChatGPT model, becomes a stochastic parrot. It's a probabilistic repetition of words in their adjacency, right? So we're going to have an exercise here in just a minute to show you that point. Of course, what's happened between the stochastic parrot and the way people interact with it is you get people like this guy at Google who thinks not only are the language models better than stochastic parrots, but they have a soul. I don't know if he's serious or if he just did this for publicity, but this is an interesting issue we will return to in the very last class. Are these things sentient? Are they actually thinking? And if so, what does that mean? He clearly believes that. And then there's this famous article by Ted Chiang talking about the language models, a kind of blurry JPEG of language itself. So this is the paper that started the whole, is there actual intelligence at the language models discussion? We will go into this in a lot of depth later, but I wanted you to see that paper and think that people are taking this question very seriously. So what can you do? Well, there's a lot of stuff you can do with natural language, right? Once you've got this capability, you can do things like take the input, classify it, and you can do sentiment analysis on that text, right? The question is how confident is it going to be? Because you can get analysis like this, that giving the valence or the value, the positive or negative aspect of this thing, it will say, here's the raw text. It will say, this is a negative comment because it's about COVID in the world, right? Awesome, we've got a sentiment analysis tool. But this is where I want you to spend 3 minutes on this, okay? So go to this. Sorry, I don't have a QR code. I guess I could generate one. Text2data.com/demo, okay? Text2data.com/D demo. Everybody got that? Spend a couple minutes on that. And it should look like this. So this is doing sentiment analysis. So try a couple of sentences of your own construction and see if it predicts the sentiment that you meant correctly. If you have a really great counterexample, I'll want to hear that.
examples of like negative intent and it says positive intent?
Well, if you've got an example, yeah.
I
Yeah.
said, for example, die please and said it's positive.
Yeah, yeah. So here's another example, kind of like that. The example I gave was, I love my new running shoes to death. I could just kill the trails in these, and it says, oh, this is pretty negative, right? Gives it a terrible score, right? Negative 0.6. See the point? See the problem here? Does anybody else have another good example? This is a good one. This is a good one. Anybody else? So an example that worked? Yeah.
The apartments we had was overall not so bad.
Okay, and how did it rate it?
Negative, -0.65.
Okay, not so bad. You mean something slightly positive. Yeah, right. This is another thing where the culture that it was, the basis it was trained on will vary, right? Some cultures are not effusive with praise. Some, like this analysis thing, is pretty English, American English based. Anybody else? A good example?
It just rated it. I mean, it just rated the phrase "most relentless threats" as positive.
Yeah. Okay, so I think you get the point there, right? I mean, there's a lot of knowledge built into these things, and so here's one that I absolutely love. This example. The text I put in was, "This is a wonderful movie. The lead actress has a vast range from A to B." Right? Remember sarcasm, irony, all that stuff? An emotional range from A to B means zip. There's no emotional range, right? But the computer doesn't understand that part. So you see the issues here. We also have problems with naming or recognizing named entities, like your name. So if you have, I will recommend this to you later. Do this later on your own. But I will point out that, actually, I'll just click to it. I'll just show it to you rather than we do it all together. So here's a sentence. And it extracted the following entities. So all these named things, Mona Lisa is a clear name, oil painting is an obvious object in the world, Leonardo is a named entity, and so on and so on. But now, suppose I change this sentence. I'm going to change it to, my friend, oops, I don't mean to yell. Okay. So let's extract this entities. Completely missed this, right? Again, the effect of the training data set. Names are particularly hard. Names are hard for every system. I've worked on, for example, a medical transcription system that would be used by physicians in hospitals. And getting words like, osteoglaucoma, or, complicated medical terms, not a problem. Getting the doctors and the nurses' names, that was a problem. So, for example, there's Dr. Eng. How do you write that last name? E-N-G, N-G. I mean, there's a million different ways to spell it, right? So it turns out the names are still really, really hard. And there's a lot of context reasons why that's so. Anyway, the point here is that this is non-trivial stuff. So here, for example, I want to talk about the UI for text spelling interventions. So this is from my book. I poured it into Google Docs and I said, hey, what do you think? And so it underlined this, right? It underlined this. It underlined this. It underlined this. So this is the UI saying, you bonehead, go fix these things, right? So what's going on here? The interaction, obviously, is that I click on the thing and it will give me preferred rewrites. The problem is this is a quote from Samuel Johnson. So knowing what books have covered it, yeah, but it's a quote, right? I can't change the quote to make you recognize you're happy. Or how about this one? This is the British spelling. Again, a quote. No, don't change that. So the human gets these options, and you have to apply your own intelligence to this. This was going to be true for a long time, I think. Or this one. Here, I wrote it this way. So I, in my American English, wrote, using a search engine to do search, I wanted to emphasize the action that you want to do it. So I'm going to reject this suggestion. Okay. Same thing, well, that's obviously a mistake. So I correct that one. And I click on more options. And now I can give feedback. We've talked about this before. Giving feedback to these systems is absolutely crucial. Right? So training, you probably know a lot of this already. The basic model for large language, way larger language models work is they predict the next word, so they do a prediction in sequence. There's a whole class on that too. But for our purposes, I want to point out that the language model actually learns more than just the predictions. It also learns things like, well, this is where the prediction would go. The what was established then. But it learns pronunciations. This is IPA. It learns geography by association. It learns agreement between vowels. It learns how to do some basic arithmetic, or at least for the numbers that it sees. And so it's picking up all kinds of interesting properties of language and encoding it in its mechanism. Again, I would love to have you play with this, but I'm going to just play with it in your stead. So this is worth, if you've got some time later this week, it's worth going to here and doing this. So I'm going to do this for you. This is basically fiddling around with predictive models. And let's do this. So I can change where the blank goes. And so it makes these different predictions based on its model, right? So let's try this. In Zürich, oops. Oh, I guess this is still changing the model. I don't want to get to it. Here we go. I can now replace the sentence here. They like to buy what? Let's update that. Things. But you can start to fool around with this and play around. And so let's contrast Zurich with, say, Amsterdam. And update. Okay, there we go. So you can see over here, the likelihood for the second sentence here in the brown is apparently they like to buy books in Amsterdam, according to this model, right? So again, reflecting that the model builds in biases and expectations. And it's this is a really useful thing for you to explore. Pardon? It doesn't surprise me at all. So there's just a warning. Some of the predictions it will make are not politically correct. Just FYI. What I want to do is flip over here. Here we go. Okay, so there's bunches of different kinds of things we can do with natural language models. Speech reco, et cetera. We've talked about all of these, but I'm just trying to give you an idea here. Oh, we're here at the end. Yeah, there we go. So I want to wind up this class by saying there's a lot of ways to interact with language online. We're going to talk about several of them over the next couple of weeks. There's no one grand unifying theory of natural language. And so what we are as a scientific field is building a bunch of different approaches. The one that we used, say, 15 years ago, it's kind of gone, right? I showed you some of the stuff in the history. We're now in a world where we have large language models, but the language models per se don't solve the discourse problem. That's where the excitement is these days. And they're not particularly well tuned to being able to support long tasks. They're constantly making hallucinations. And as you saw in an example earlier, they will do stupid things like tell you can buy a car for $1, right? We want to figure out how do we control these things in order to use them effectively for our tasks. So there are lots of things you can do. There's a lot of exciting research to do in this area. And let's go to our question for today.